So moving away from LU decomposition, we are going to consider another special method or algorithm in solving a system of linear equations, and we call that the Cholesky Decomposition Method. Now, the Cholesky Decomposition Method is basically used to decompose a symmetric positive definite matrix into the product of a lower triangular matrix times its transpose. That is, A is equal to H times HT, where A is said to be the coefficient matrix, H is the lower triangular matrix with positive diagonal entries, and then HT is basically the transpose of H. Now, from the definition of Cholesky decomposition, the decomposition is made possible if and only if the following two conditions are satisfied. That is, one, if the coefficient matrix is symmetric, that is, if A is equal to A transpose, and then secondly, if the coefficient matrix is positive definite. Now, so long as these two conditions are satisfied, then we can decompose the coefficient matrix A so that we have H times H transpose. So given a system of n linear equations with n unknowns, let's look at how we can solve that system. So first of all, we are going to represent the system in the form Ax equals b, where A is the coefficient matrix, x contains the unknown variables x1, x2, x3, and then b is the constant we see on the right hand side of each of the equations. And then so long as these two conditions are satisfied, then we can decompose A so that we have H times H transpose. Now we substitute this into the original equation so that we have H times H transpose times x, and that is equal to b. Now we are going to let H transpose times x be equal to y. We substitute this, that is, we substitute y in place of htx in here, and then we are going to have hy equals b, and we call this our first equation. So we solve this equation for y, and then we substitute the values of y into this second equation, and then we try to solve for x, which becomes the solution vector. So basically, this is the solution process to solving a system of linear equations using Cholesky decomposition method. So we have an example here. Let's try to solve this example together. So first of all, we need to represent this system in the form Ax equals b. So we have the coefficient matrix having elements 4, 2, 14, 2, 17, negative 5, 14, negative 5, 83, and then we have the column matrix containing the unknown variables x1, x2, x3, and that is equal to the constant matrix. We have 14, negative 101, and then 155. Now the next thing is we need to decompose this coefficient matrix so that we have a lower triangular matrix with positive diagonal entries times its transpose. Now to do so, we need to check and see if A, which is the coefficient matrix, is symmetric and positive definite. So considering the first condition, that is whether A is symmetric, we need to check if A is equal to its transpose. So we have matrix A, which has elements 4, 2, 14, 2, 17, negative 5, 14, negative 5, 83. Let's see if this is equal to A transpose. So for A transpose, to find A transpose, we are basically going to make sure that each row becomes a column here. So here we have 4, 2, 14 here for row 1. So we are going to make sure that this becomes column 1. So we have 4, 2, 14 becoming an entry for column 1. And then for column 2, we have 2, 17, negative 5. Column 3, we have 14, negative 5, 83. So for the transpose, you basically make sure that each row becomes a column. Now let's compare the values in here. You realize that what we have on the left hand side, or the matrix on the left hand side, is equal to the matrix on the right hand side, which means that A is equal to A transpose. Hence, the coefficient matrix A is symmetric. Now let's move on to the second condition. Now for the second condition, that is the matrix A should be positive definite. It should be positive definite. Now A will be positive definite if the determinants of the sub-matrices starting from the top left are all equal to 0. So we are going to break down this into sub-matrices, and then we are going to consider or see if these sub-matrices have determinants greater than 0. So we have our first sub-matrix, and we call that A1, and that is equal to a 1 by 1 matrix, which is 4, starting from the top left. So we have 4 here. This is a 1 by 1 matrix, and then we try to find the determinant of this 1 by 1 matrix, and that is simply the same value, 4, and this 4 is greater than 0. Now let's move on to the second sub matrix, that is a 2 by 2 matrix. So we consider this 2 by 2 matrix. So it has elements 4, 2, 2, 17. So let's try to find the determinants of A2, and that will be equal to, we multiply these two values, 4 times 17, we have 68, minus 2 times 2, that is 4, and this is equal to 64, which is also greater than 0. Now we move on to the third submatrix, which is basically A3, and that is simply equal to A, the original matrix. So you are going to have components or elements 4, 2, 14, 2, 17, negative 5, 14, negative 5, 83. Let's try to find the determinants of this matrix A3. So the determinant of A3, that is simply, so we select the first element, that is 4, and then we try to cancel out the row and column containing this element. We multiply 83 by 17, we have 1, 4, 1, 1, minus, we have negative 5 times negative 5, which is 25, so minus 25. Next element for the same row, that is 2, so minus 2. So we cancel out the row and column containing that element. We have 2 times 83, that is 166, minus 14 times negative 5, that becomes negative 70. So negative negative becomes positive, and then plus last element for the same row, we cancel out the row and column. We have negative 5 times 2, that is negative 10, minus, we have 14 times 17, and that also gives 238. So when you compute this, you are going to have 1600, which is also greater than 0. So since the submatrices have determinants greater than 0, in fact all of them have determinants greater than 0, it follows that the coefficient matrix A is positive definite. The coefficient matrix A is positive definite. So we also have a correct here. Now since the two conditions are satisfied, then it means that we can do Cholesky decomposition. Cholesky decomposition is possible. So we are going to decompose the coefficient matrix so that we have a lower triangular matrix with positive diagonal entries times its transpose. So let's do that. So we are going to have, or we are going to do the decomposition A equals H HT. So we are going to have the coefficient matrix 4, 2, 14, 2, 17, negative 5, 14, negative 5, 83, and that should be equal to a lower triangular matrix. We are going to have H11, H21, H22, H31, H32, and then H33. And then we have the rest of the elements to be 0, 0, 0 times its transpose. So row becomes column. We have row 1 becomes column 1. So H11 0, 0. Row 2 becomes column 2. H21, H22, 0. Row 3 becomes column 3. H31, H32, H33. Now, here we have 6 unknowns, and we need to find all the 6 unknowns. So here we are going to use what we call the Cholesky algorithm to find each of the 6 unknowns. Now, from the Cholesky algorithm, that is given by this formula, that is HKI is equal to that, and HKK is also equal to that. For k equals 1, 2 through to n, and then for I equals 1, 2 through to k minus 1. So if you have the same row and the same column, that is the same row value and then column value, then you are going to use this expression. And then if the row value is not equal to the column value, you also use this expression. So from this algorithm, we are going to find the 6 unknown elements. Now notice that when solving for the unknowns, we usually solve row by row. However, for the sake of this lesson, we are going to solve column by column. Also notice that k here represents the number of rows, and then I also represents the number of columns. Now in respect of that, we are going to consider the first column. So that is for I equals 1. So you are going to try to find the values of H11, H21, and then H31 for the first step. So for the first element, we have H11. This simply means that we want to find element of row 1, column 1. So we come to the Cholesky algorithm. We are going to use H11. So that is simply equal to, we are going to have the square root of A11, okay, minus, we have the summation of this formula from j equals 1 to k minus 1. Don't forget that we have k to be 1. So if k is 1, then here becomes 0 on top here. So we have the summation of this formula from j equals 1 to 0. Now the moment we have from j equals 1 to 0, it means that this whole term goes to 0. So simply we can say that H11 is simply equal to the square root of A11. So that is the square root of element A11, and then A11 is equal to 4. So we have the square root of 4, that is equal to plus or minus 2. Now since the diagonal entries is to be filled with elements, or is to be filled with positive elements, we are going to ignore the negative and then we consider the positive value. So we have H11 to be equal to 2. Now for the same I equals 1, let's consider H21. So for H21, we are going to have or find elements of row 2, column 1. Now using the same algorithm, the Cholesky algorithm, okay, we are going to use this one, and then we are going to have A21 divided by H11. That is from the algorithm. Now we have A21 to be 2 divided by H11, which is also 2, and thus we have a 1 here. Now we move on to H31. Still using the same algorithm, we are going to have A31 divided by H11, and that is simply 14 divided by 2, and that is equal to 7. So now we've been able to find elements of the first column. Now let's move on to elements of the second column. So we are going to have, for I equals 2, we are going to find the element H22. So from the algorithm, from the formula HKK, for H22, we are also going to have the square root of A22 minus H21 squared. So that is simply equal to, we have the square root of A22, that is 17. So 17 minus H21 is 1. So we have the square of it, so 1 square, and that will be equal to the square root of 16, which is equal to plus or minus 4. Now, since H22 is an entry in the principal diagonal, it means that we are going to select the positive value, only the positive value. Now let's move on to H32. So for H32, from the algorithm, you are going to have 1 over H22 all times A32 minus H21 times H31. So that will be equal to 1 over H22 is 4 into brackets A32, that is negative 5. So negative 5 minus H21, that is 1, times H31, 7. So this becomes 1 over 4 times negative 5 minus 7, that is negative 12. So 1 over 4 times negative 12, that becomes negative 3. Now let's move on to column 3, that is for I equals 3. So for I equals 3, for the third column, we only have the element H33. So we have H33, and according to the algorithm for HKK, we are going to have the formula that is given by the square root of A33 minus H31 square minus H32 square. So that is simply the square root of 83. So A33, 83 minus H31 square. H31 is 7, so 7 square, that becomes 49. So minus 49, and then minus H32, that is also negative 3. So negative 3 square is 9, so minus 9. And then 83 minus 49 minus 9 is simply 25. So we have square root of 25, and then because we want the positive value to fill the principal diagonal entry, then we are going to have a positive 5 here. So we've been able to find the values of all the 6 unknowns, Therefore, we have the coefficient matrix A to be equal to H, which is given by, we have H11 to be 2, H21 1, H31 7, and then we have a 0, H22, that is 4, H32 negative 3, and then we also have 0 0, and then H33, that is 5. So this is H, and then times H transpose. So row becomes column, like we've already done here. So we are going to have 2 0 0, row 1 column 1, row 2 column 2, 1 4 0, row 3 column 3, 7 negative 3, 5. So basically this is the decomposition from A into H times H transpose. Now the next thing we are going to do is to solve equation 1 for Y, and then equation 2 for X. So for equation 1, we have HY equals B. HY equals B. So for HY equals B, that is equation 1. For H, we have the elements 2 0 0, 1 4 0, 7 negative 3 5. So 2 0 0, 1 4 0, 7 negative 3 5 times y1 y2 y3, and that is equal to B, the constant matrix, which is also 14 negative 1 0 1 155. So 14, negative 101, and then 155. So let's try to find the values y1, y2, and then y3. So we are going to do forward substitution. y1 corresponds to column 1, y2 column 2, y3 column 3. So here we have 2 times y1. Notice that the 2 zeros here have no effect. 0 times y2 is 0, 0 times y3 is also 0. So we have 2y1, and that is equal to 14. So we divide through by 2, and then we have y to be equal to, sorry, y1, we have y1 to be equal to 7. Now let's move on to row 2 to find y2. So here we are going to have 1 times 7. So 1 times y1, 1 times 7, plus 4 times y2, plus 0 times y3, and that is equal to negative 101. So here we are going to have 4y2, and that is equal to negative 101 minus 7, and then 4y2 equals negative 108. So we divide through by 4, and then we have y2 to be equal to, 4 goes here once, 4 goes into 10, 2 times remainder 2, 4 goes into 28, 7 times. Therefore we have negative 27. That is the value of y2. Now moving on to y3. From row 3 we are going to have 7 times y1, which is 7, and then minus 3 times y2, which is negative 27, plus 5 y3 equals 155. So here we are going to have 49, negative negative positive, so plus 81, plus 5 y3 equals 155. On the left hand side we are going to have 49 plus 81, which is 130, plus 5y3 equals 155. You transpose this to the right hand side, we have 5y3, that is equal to 155 minus 130, and that is equal to 25. We divide through by 5, and then we have y3 to be equal to 5. So basically this is the value of y3. Therefore we have y to be equal to y1, y2, y3, and that is equal to, we have y1 to be 7, y2 negative 27, y3 that is 5. Next we are going to substitute the values of y into equation 2 so that we find the values of x, or we find x. So that is htx, or h transpose x equals y. So this is h transpose 21704 negative 3 005. So for h transpose x equals y, which is equation 2, we are going to have 21704 negative 3 and then 005 times x1, x2, x3 equals the values of y, that is we have y1 7, y2 negative 27, y3 that is 5. Here we are going to do back substitution. So here also x1 corresponds to column 1, x2 column 2, x3 column 3. So we are going to have 5x3 equals 5. So 5x3 equals 5. We divide through by 5. We have x3 to be equal to 1. To row 2, we are going to have 4x2 minus 3 times x3, which is 1, equals negative 27. We have 4x2 equals negative 27 plus 3, which is equal to negative 24. So we divide through by 4. We have x2 to be equal to negative 6. This is the value of x2. Now we move on to the last, or basically row 1. And then here we have 2 times x1 plus 1 times x2 plus 7 times x3, and that is simply equal to 7. So here we have 2x1 minus 6 plus 7 equals 7. This becomes 2x1 equals 7 minus 7 plus 6, and that is equal to 6. So we basically divide through by 2, and then we have x1 also to be equal to 3. Therefore we have the solution vector x to be equal to the column matrix x1, x2, x3, and that is equal to x1 3, x2 negative 6, x3 1.